નમસ્કાર વિદ્યાર્થી મિત્રો, આજના આ સ્ટેટિસ્ટિક્સના સેશનમાં આપ સૌનું સ્વાગત છે. ગયા સેશનમાં આપણે કન્ટિન્યુઅસ ડિસ્ટ્રીબ્યુશન્સ વિશેની સમજ કેળવી અને એમાં ઘણા બધા કન્ટિન્યુઅસ ડિસ્ટ્રીબ્યુશનની પણ ચર્ચા કરી, એના ઉપયોગો વિશે પણ આપણે જાણ્યું, જેમાં ખાસ કરીને યુનિફોર્મ ડિસ્ટ્રીબ્યુશન, રેક્ટેન્ગ્યુલર ડિસ્ટ્રીબ્યુશન, બીટા ટાઈપ 1, 2, એક્સપોનેન્શિયલ, ગામા અને કાઈ સ્ક્વેરની થોડીક વિગતો આપણે આપી અને કદાચ તમને એ ઉપયોગી નીવડી હશે. એ જ પ્રમાણે આજના આ સેશનમાં આપણે નોર્મલ ડિસ્ટ્રીબ્યુશન, એના ઉપયોગો, એની કેરેક્ટરિસ્ટિક્સ વગેરે ઉપર ચર્ચા કરવાના છીએ. અને સ્ટુડિયોમાં એ માટે આપણી સાથે પ્રોફેસર એસી શાહ, જે મારી બાજુમાં બેઠા છે, અને વિદ્યાનગરથી આવેલા અંકિતભાઈ સિનોજિયા, એ આપણને નોર્મલ ડિસ્ટ્રીબ્યુશન વિશે વધારે માહિતી આપશે. પ્રોફેસર શાહ સાહેબ છેલ્લા 28-30 વર્ષથી ભાવનગરની સર પીપી ઇન્સ્ટિટ્યૂટમાં આંકડાશાસ્ત્રના અધ્યાપક તરીકે સેવાઓ આપે છે. તો આપણે એમના તરફથી આ નોર્મલ ડિસ્ટ્રીબ્યુશન શું છે, એની ઉત્પત્તિ, એની જેનેસિસ શું છે, એના વિશે સમજશું. પણ એ પહેલાં થોડીક ઇન્ટ્રોડક્શન હું એ માટે આપી દઉં, એક પૂર્વ ભૂમિકા તરીકે. તો એક ફ્રેન્ચ ફિઝિસિસ્ટે સાચું જ કીધું છે કે એવરીબડી બિલીવ્સ ઇન ધી નોર્મલ એપ્રોક્સિમેશન. The experimenter believes because they think it is a mathematical theorem, and mathematicians believe that it is the experimental fact. અને આ જ કંઈક પૂર્વ ભૂમિકા સાથે આ નોર્મલ ડિસ્ટ્રીબ્યુશનનો અસ્તિત્વ ઉદ્ભવ્યું એવું હું કહી શકીશ, તો એમાં કંઈ ખોટું નહીં હોય. ડ્યુરિંગ 17th century, સ્વિસ મેથેમેટિશિયન જેમ્સ બર્નોલી, તમે જે બર્નોલી ડિસ્ટ્રીબ્યુશન ડિસ્ક્રીટ કેસમાં જોયા એની આ થોડીક વાત છે, succeeded in giving the rigorous proof of the law of averages. And according to him, if a coin is tossed a large number of times, it lands heads will be closer to the value 50%, which is with the high probability. And this finding was remained unaltered for almost 20 years. Then after, in 1733, De Moivre has developed and introduced a new concept, and on the basis of that he showed that binomial distribution was a very closer to the normal approximation. And on the same line, Gauss જેણે નોર્મલ ડિસ્ટ્રીબ્યુશન, નોર્મલ કર્વનો એસ્ટ્રોનોમીમાં ખૂબ જ મોટા પ્રમાણમાં ઉપયોગ કર્યો, અને ખાસ કરીને જે ડિસ્ટ્રીબ્યુશન ઓફ એરર્સ છે એના વિશેની એને જે સમજ આપી અને નોર્મલ ડિસ્ટ્રીબ્યુશનનો ઉપયોગ એમાં કર્યો, એ વિશે આપણે વધુ વિગતો દ્વારા પ્રોફેસર એસી શાહ સાહેબ પાસેથી સમજશું. તો શાહ સાહેબને હું વિનંતી કરીશ કે એમનું આગળ નોર્મલ ડિસ્ટ્રીબ્યુશન વિશે માહિતી કંઈક આપણને આપે.
થેન્ક યુ સર.
અને સાથે સાથે આપણે સ્લાઇડ પણ જોતા જઈશું, એટલે જ્યારે પણ સ્લાઇડની આવશ્યકતા હશે ત્યારે આપણે કેમેરા દ્વારા સ્લાઇડ પણ જોઈશું અને સાહેબને પણ સાંભળશું.
My dear students of statistics across all science colleges in Gujarat, I will just first of all congratulate you for selecting a very fascinating field of statistics. Statistics is really highly applicable science, and there are many applications across many areas. Normal distribution is a very prominent distribution, and we start with the first slide. Let us see. This is our institute, Sir P.P. Institute of Science, where I come from. Now, my dear students, in probability and statistics, there are two types of random variables. Now, there is a difference between variable, simple variable of mathematics and random variable. You know that random variable takes values or assumes values with a probability concept. So, actually statistics is built around uncertainty, where probability comes into picture. So, random variable is a variable. In fact, it is a function which is defined on a sample space that you perhaps know. Okay, so there are two types of variables, random variables, discrete and continuous. For example, I will give you a very straight example. For discrete random variable, say if you visit different families in a certain area, and if you ask every family how many children are there, so number of children will be 0 or 1 or 2 or 3. It cannot be fractional. So that is discrete. While if you consider, if you make the study of heights of students or heights of soldiers in a battalion, that you see that height can take any value inside a real interval. So that is a continuous variable. So there are probability models developed for discrete variables, and there are also very good probability models designed for continuous random variables. For continuous random variables, we have several distributions, as just Gajar sir told you: uniform distribution, exponential, gamma. But the prominent distribution in continuous case is normal distribution, because of its applicability in a variety of situations in real life. So you can see the curve on the first slide. It's a bell-shaped curve. If you consider the heights of any person, see the lower side, there will be few persons. There will be many persons in the center of the curve, and there will be very few with high eyesight. That is, with a tall persons. They will be also very few. Okay, let us now go to the first slide. A random variable whose space is countable or finite is discrete. This is the technical definition of discrete variable. And for continuous there are some lines you can see whose space is uncountably infinite, that is called continuous. Okay, next slide. Now, basic difference between discrete and continuous random variables is for discrete random variable you can find probability for a random variable takes a particular value, while for continuous case we cannot find probability of a variable taking a particular value. If you put, suppose fx is the probability density function, if you put x equal to a, you will get the length of the ordinate. That will be clear in the next slide, perhaps, or still next. Okay. Now, fx is qualifies to become a probability density function if it satisfies two conditions. It must be greater than or equal to 0 for all values of x, real values, and probability that random variable x takes any particular, x takes any interval value, in an interval, that is AB, probability that a less than x less than b, you can find it out using integrating the function fx over the range a to b. It's a definite integral. So geometrically you can see on the slide that it is the area under the curve fx between the two ordinates, one at x equal to a and other at x equal to b. So that way, in case of continuous random variables and continuous probability density function, it is meaningful if you want to find probability of an interval. This is the basic difference between discrete case and continuous case. Okay. Now next slide please. Normal distribution is very prominent, as I have told you, continuous model. You can apply it in a variety of situations, a variety of sciences. Several applications are there in physical sciences, in biological sciences, in economics, in commerce and industries, and also in behavioral sciences like education, etc., psychology, sociology, etc. So, let us go to the history of normal distribution. Normal distribution was investigated in the 18th century when scientists worked in the field of astrophysics. Prominent among them was Gauss, and I will tell you something about Gauss also. Gauss was a French man, and he was the son of a peasant, a very poor peasant. And at the age of 3, Gauss, and we can see the picture of Gauss also. It is on the extreme left, Gauss. There is a note on which the picture of Gauss is there, He was a German person and very well known. He has contributed in several areas, but if you see his childhood, at the age of 3, he mentioned a mistake in the calculation of his father. His father was a peasant, and he was very brilliant from his childhood, and therefore his father was persuaded to let him study. Although they could not afford the education of gas, but still he was persuaded, and he was born in Brunswick County in Germany, Brunswick County. The Chancellor of Brunswick gave him a scholarship so that he could learn in a high school and college. And at the age of 18, he proved a very fundamental theorem of algebra. He has contributed in the field of astrophysics also, and moreover he has contributed in the field of statistics. Actually, by way of 2 contributions are there. One is normal distribution. He has made very fundamental work in the field of normal distribution, and the other is method of least squares. Method of least squares is also due to Gauss. The other 2 are Laplace and De Morgan. Their pictures are also there. You can see on the slide. They have also worked in this field, normal distribution. Okay. Now I will explain something on the board also. Next slide, please. So Carl Gauss undertook the fundamental work with the normal distribution, and the form of the definition of the normal distribution. As you can see on the slide, that fx equal to 1 upon sigma root 2 pi e raised to minus x minus mu whole square upon 2 sigma square. In fact, x is the variable, normal variable, and mu and sigma are 2 statistical parameters. These 2 pi and e are mathematical constants, and the variable can take any value on the real line. And these 2 parameters, mu can take any value from minus infinity to infinity, and sigma is strictly positive. Sigma is strictly positive. So, in fact, this is the format of normal distribution. It is continuous, and if you draw the curve, you can draw the curve provided you know mu and sigma. If you know mu and sigma, this distribution is totally specified, and computer can also plot the graph, and it is a very bell-shaped ideal curve, where you can see that this is actually the graph of fx. This can be drawn provided you know mu and sigma, and mu is the center. The highest ordinate you can see, it occurs at mu, highest ordinate. Now these values, actually theoretically it can take any value from minus infinity to plus infinity, but practically speaking, most of the area is covered between mu minus 3 sigma and mu plus 3 sigma. Now we will see in the properties also that mu will be the mean of the normal distribution, and sigma is nothing but the standard deviation. Okay, so practically speaking, most of the area of this curve is covered between these 2, mu minus 3 sigma and mu plus 3 sigma. Right? Theoretically it runs from minus infinity to infinity. Okay. Now the next property we will see on the slide. The normal distribution is a continuous probability model. It has 2 parameters, as I have told you. Graph is also there. The maximum ordinate is this one, and this occurs at x equal to mu. And if you put x equal to mu in the formula, you will get 1 upon sigma into root 2 pi. So maximum ordinate, fx maximum value of fx is 1 upon sigma root 2 pi. Okay. The next property is, okay, it is symmetric, as you can see. Symmetricity concept has been explained. Suppose you go distance t on the right side, say mu plus t. and the same distance on the left side of mu, that is mu minus t. Now these two, as you can see on the graph there on the slide, that f of mu plus t, this is in fact f of mu plus t. F of mu plus t, substitute x equal to mu plus t in the formula and you will get a result, and substitute x equal to mu minus t in this formula and you will get the result. Both will be exactly equal, and therefore you can see that these two ordinates are same. The curve is bell shaped. I think, my dear students, you must have seen the bronze bell in your college. If you cut that bell from the middle and if you put it on a desk and if you make an outline, it seems like this. It's exactly bell shaped. It is very symmetric, and symmetricity concept is this: whatever distance you go on the right side, same distance you go on the left side, the two ordinates, means the two sticks, will be exactly same. That's the symmetricity concept. The next characteristic will be, so population mean, median and mode of normal distribution, they are identical and they are same, and the same value is mu. Of course, the mean, etc., median, etc., we can compute and they all come out to be equal to mu. Okay. Now median means, mu means what? The half portion, the curve is divided exactly at this stage. The curve is divided 50% on the left side and 50% on the right side. Therefore mu is the median of this distribution, of course. Now mean, median and mode are same. Next. Okay. The curve, normal distribution is based on these two parameters, mu and sigma. So sigma, as I have told you, will be standard deviation. We can prove it. Sigma is nothing but standard deviation. Mu is nothing but mean of this distribution. So there are two pictures you can see on the slide. One normal distribution is with mean 60 and standard deviation 4. It is sigma square is equal to 16. Sigma square is called variance, and sigma is standard deviation. So sigma is 4, you can see in the first normal distribution. And in the second distribution, y, the mean is 130 and sigma is 3. So look at the pictures of normal. If sigma is more, the curve will be spread more. The spread will be more. So sigma indicates the spread. Sigma is the measure of spread of this normal curve, and mu indicates the centering, where the curve is centered. Okay, so these two things are to be noted. Of course, the bell shape will be preserved. Whatever will be the value of sigma, bell shape is going to be preserved. There is no problem about it. Okay, next slide. Here again the same thing. Sigma values are different. If sigma is more, the curve is more flattened, and if sigma is less, you can see different pictures are there. Normal shape is everywhere, and you can see if sigma is less, you can see the curve is very synchronized, very compact in that sense. Okay, next. Now we can see that all odd order central moments. Now central moments, as you know, is defined. If you want to find out rth order central moment, it is expected value of x minus mu1 prime raised to r. So in fact, it's a moment about mean. Mu1 prime is, perhaps you know that mu1 prime is mean of the distribution. So this is the rth order central moment. Now in normal distribution, all the odd order central moments are 0. That can be proved. So mu1 is 0, that is true. I think you know that mu1 is 0, that is true everywhere. But what is the speciality of normal distribution? That mu1 is 0, mu3 is 0, mu5 is 0. In fact, mu2n plus 1 is 0. Now this also can be proved very easily, and this comes from a basic odd function property of integral. It comes in 3 steps merely. Okay. But we can find even order moments, even order central moments. There is a formula on the slide. That is mu2n. It will be the next I think in the next slide. Mu 2n is 1, 3, 5, 2n minus 1, sigma raised to 2n. That is even order central moments we can find out. Using this formula we can find out mu 2, and mu 2 is second central moment. It is sigma square, and mu 4 is 3 sigma raised to 4. In fact, mu 1, mu 3, mu 5, they are all 0. So beta 1, if you want to find out, beta 1 is skewness coefficient. So beta 1 is mu 3 square upon mu 2 cube. This is the formula. And mu 3 is 0, therefore beta 1 is 0. Beta 1 is 0 means the curve is neither positively skewed nor negatively skewed. It is very much symmetric. It is very much symmetric. So beta 1 greater than 0 means, suppose some curve may be like this. This is not normal. Here you see that the right tail is extended more on the right. This tail, right tail is extended more compared to the left, and therefore here beta 1 should be greater than 0. In fact, root beta 1 should be greater than 0 in this type of. And for negatively skewed distribution, root beta 1 will be less than 0. This is neither positively skewed nor negatively skewed. It's exactly symmetric. Okay. We can find also the moment generating function of normal distribution. The moment generating function of normal distribution, it is equal to, you know, moment generating function mxt. It's a function of t, and it is defined as expected value of t raised to tx, where t is any real number. It can be any real parameter. This is the basic definition of moment generating function. And moment generating function may exist, but in case of normal it does exist, and it is equal to e raised to mu t plus 1/2 t square sigma mxt. In case of normal, if x follows, now there is a symbol, x follows normal distribution, these two parameters mu and sigma square, mxt will be equal to e raised to mu t plus 1/2 t square sigma square. Now this also can be derived, very simple to derive, and for that we will derive it provided we have time later on. Okay, let us go to the next. Characteristic function is also mentioned. Now in characteristic function, just to replace t by it, you will get the characteristic function. And next property is ninth property, that is linear combination of independent normal variables is also a normal variable. Suppose x1, x2, x3, they all are normal. Now normal distribution you can apply in a variety of situations. You can apply x1 is the random variable corresponding to IQs of first college. I will give you a very simple example. x2 means IQs of the second college, and x3 means IQs of students of the third college, and they all follow normal distribution with different parameters. And suppose they are independent. Suppose they are independent. Now if you make any linear combination of them, a1, x1, this will be a new variable. It will be a new variable, and it will also follow normal distribution, and their means and variances we can find out. Means mean of this fellow, mean of this function, and mean of variance of this function we can find out. Okay. So it is indeed follows normal distribution. So it's a linear combination of three independent normal random variables. This is a very good property which we can use in inference also. Normal distribution is applicable, as I have told you, in inference also, statistical inference, and in quality control also. My dear students, you must have studied mathematical statistics, some part of mathematical statistics, in which there is a theorem, basic theorem, very fundamental theorem of mathematical statistics. If somebody asks you, which is the fundamental theorem of mathematical statistics, it is, you know, central limit theorem, CLT, central limit theorem. So central limit theorem, if you see the statement, it is also pertains to normal distribution. Even if you take sample from any distribution, maybe gamma, maybe exponential, maybe any sort of any other unrecognized type of distribution may be there. And if you take a sample x1, x2, xn from this population, okay, x1, x2, xn, they are random variables. If you provided your sample is large, sample mean will follow normal distribution irrespective of the population distribution. That's a very nice property of normal distribution. CLT says this, and which we are using in quality control, statistical quality control. That's a basic statistical principle of quality control, where we draw certain X bar chart, R chart, etc. There we make use of this fact also, CLT property. Okay. So normal distribution is applied in design of experiment also. We will see in the next lecture perhaps. Okay, next slide please. Okay, this is a very, very important property of normal distribution, that actually if somebody asks you how many normal distributions are there, because mu and sigma square, it depends on mu and sigma square. So you can select mu in how many ways? You know, mu can be selected in an infinite way, number of ways, and sigma also can be any positive value. So mu and sigma both can be selected in an infinite number of ways. So we have an infinite number of normal distributions. So if you want to compute certain example, you cannot prepare tables for all normal distribution. It is not possible. And therefore, this is a very important property. From any ordinary normal distribution, you can go to standard normal variable. This is the ordinary normal variable. Now, suppose mean is 60 and sigma square is 9, suppose. Let me tell you. Mu is 60 and sigma square is 9. Then x minus mu upon sigma, that is equal to x minus 60 upon 3, because sigma is 3. This is a special, this is called a special variable. It is called standard normal. And we can prove that by using MGF technique. We can prove that this is a new random variable, Z, and Z is called standard normal variable, and it also follows normal distribution with mean 0 and variance 1. With mean 0 and variance 1. This, here you can check that both the parameters are totally known. The structure of this Z is, probability distribution of Z is totally, completely known. So any ordinary normal random variable can be converted to Z. Okay. Now Z probability density function is, you know, Fz is equal to 1 upon root 2 pi e raised to minus Z square by 2. Minus infinity less than Z less than infinity. Now check that here there is only variable Z. Pi and e are mathematical constants. So this function is totally identifiable, recognized. We can draw, computer can plot the graph, and the graph also is bell shaped. Centering is at 0. Of course the Z takes any value from minus infinity to infinity, and it is bell shaped. We can see on the slide also. Standard normal structure is 1 upon root 2 pi e raised to minus Z square by 2. It is totally known. Next slide please. And this is the graph. Now at these are the values of Z. And at Z is equal to 0 you get the maximum ordinate, and we can see on the graph that it is slightly less than 0.4. At Z is equal to 0, the ordinate is slightly less than 0.4. And the values, most of the values you can see are covered between minus 3 and plus 3. Standard deviation being 1. What is the standard deviation of Z? It is 1. And therefore, most of the values will be covered between minus 3 and 3. Between minus 3 and 3, 99.73% of the area is covered. Okay. And this principle is used in the control charts also. 99.73% area is covered between minus 3 and plus 3. Okay. Now, this is also symmetric. Mean is 0, median is 0, mode is 0. Of course, it is bell shaped. Okay. And if you want to find, there is a very interesting property. that first of all, if you want to compute examples related to normal distribution, it's ordinary normal converted to standard normal. Standard normal is totally known. We have prepared tables. We have got tables for standard normal, cumulative standard normal distribution. So there are, first of all, we will see that if you want to find probability that minus infinity less than z less than infinity, okay, so this can be mathematically this is this, and geometrically it is the total area under the curve. It is the entire area under the curve, standard normal curve. It is called, this one is called standard normal curve. So it is total area under the standard normal curve, and because it is PDF, it must be equal to 1. Every PDF satisfies. If you integrate a PDF over the entire range, it must be 1. So total area is 1. Now 0 is median also. As I have told you, it is mean, median and mode. That is 0. So 0 is the centric or median. So half of the area will be to the left of 0, and the remaining half area will be to the right of 0. So you can see that probability that minus infinity less than z less than 0, that will be 1/2. And on the right side, this is to the left of 0, and this is to the right of 0, it is also 1/2. Means median is 0. It divides the distribution in exactly 2 equal parts. Okay. Now this is the symmetricity and bell shape, etc. also there. But there is a very interesting area property. So if you want to find, this is standard normal curve. Okay. Now suppose you want to find this sort of, what is the probability that probability minus infinity less than z less than 1.3. So where will be 1.3? Of course 1.3 will be on to the right of 0. These are the values of z. So I want this probability of this specific interval minus infinity to 1.3. This shaded area is this much. So we have got tables available for this sort of, to find out probability of this sort of interval. We will show the tables. And I have got a table here with me. This is the first page. On the first page, minus values have been tabulated. Minus values of z have been tabulated. And on the second page, positive values of z have been tabulated. Okay. So there, I have got a PDF file of cumulative standard normal distribution also. We will see later. We can use the table to manipulate any type of probability. If you want to find out, we can find out. Let us see example number 1. On the slide. So okay, these properties I have met as I have narrated, and this the fourth property also you mark, that is the C to any value C. Because of symmetricity. This much. Suppose let me take 1.1, and this is 1.1. So 0 to 1.1 if you take this area, and this area if you consider on the left side, they will be exactly same due to symmetricity of the standard normal curve. Okay. Next slide please. This is a table, as I have discussed, tables of areas for the standard normal. This table is available for positive values of z. So it gives you area from minus infinity to some positive value. Minus infinity to some positive value. And there are also other tables available for minus infinity to some negative value. Now this table can be used in 2 ways. We will see in examples. Let us start with the examples. So example number 1, if you can check that given z is a random variable, this standard normal random variable. In fact, it is having standard normal distribution. Find probability Z less than 1.33. So less than 1.33, you draw the picture. This is 1.33 is somewhere here. This is 0. And you want this area. Minus infinity less than Z less than 1.33. This to the left of 1.33. Table will give you this area, and we have recorded that. Okay, that value comes out to be equal to 0.90 something. 908. Okay. Now the second problem is Z greater than minus 0.79. So this is in fact the manipulation of the properties of standard normal, and using the table in our way. This is 0, so minus 0.79 may be somewhere here, and you want Z greater than minus 0.79, means to the right of this, so you want this much area. So now tables are available for minus infinity to minus any value or positive any value. Tables are available. How will you find this area? For that, if you want to find Z greater than minus 0.79, in fact it is equal to, because we know that minus infinity to infinity, that area, that is already known, minus this area which is available from table, minus 0.79. So, in fact, we know from the property that total area under the curve is 1 minus this area which is available from your table. For minus value, as I have told you, there is a different place. So 1 minus table area you can get it from table, corresponding to minus 0.79. Okay. The next is also similar examples are there, but this table can be used in a reverse way also. Suppose in this way, I will explain. Suppose this is standard normal curve, and as you know, this is 0, centering. Now these tails do not touch x-axis, they never touch x-axis, this is infinity. Okay, and suppose this area some value Z0 you want to find out, suppose, and you want this probability 0.67. Suppose this is the area. Probability is given and Z0 you want to find out. That's a reverse problem. So in fact you know that this is 0.67. Now first decide that from minus infinity to 0 the area is 0.5. Now this probability or this area is more than 0.5, so obviously your Z0 must lie to the right of 0. It must be to the right of 0. This is a factor. Whether this probability is greater than 0.5 or less than 0.5. If it is greater than 0.5, your variate value must be to the right of 0. Okay? In contrast, suppose you want to find out some other value, say Z1 maybe, and suppose the area is 0.36. Now you see that this area is less than, probability is less than 0.5, so your Z1 must fall on the left side. It must be negative in that sense. So which page to be used? There are two pages, one for negative values, one for positive values, and for 0.67 just you go to the second page of the table. In this table I brought 0.67. If you see corresponding value you can get of Z0. So it's a reverse procedure actually. 0.67 we have to locate inside the table, inside the body of the table. We will find out 0.67, and correspondingly we will go out and trace the value of Z, and that is, you know, it is 0.44. So Z0 is 0.44. So this is the reverse use. This table can be used in either of the two ways. One, if Z is given, some varied value is given, and some area with probability you want to find out, that also is possible. And the reverse way, corresponding to area, we can find the varied value also. Now let us go to example number 3. Example number 2 is also a similar type that we have mentioned. Now example 3. In example 3, it's an application related to life of certain product, transistor, transistors are in electronic equipments. So a company produces transistors. It supposes the mean lifespan is 100 hours with standard deviation 20 hours. So mu and sigma both are known from the past experience. The manager does know something about mu and sigma from his experience. So it says that it is 100 hours and this is suppose 20 hours. Sigma he does know. Okay. Now if you know both the parameters, you can answer any sort of question related to normal distribution. So what is the first question? Next slide. So first question is, if you buy a new transistor from the market of this company, what is the probability that your newly bought transistor will last more than 75.6 hours? So in fact, your question is, I will explain. First question I will explain. X is normal. You know mu is equal to 100, average life, and standard deviation, as you know, is 20 hours. It is standard deviation. Standard deviation has got the same unit as X. Mu has also got the same unit as X. But sigma square unit, if you want to find sigma square, it is 20 square and it is 400 hours square. Please bear in mind. Sigma square unit is hour square. Okay, these two parameters are totally known. Therefore, let us go to Z, usual procedure, because we have to go to standard normal to make use of table. So x minus mu upon sigma, this is the transformation. So x minus 100 upon 20, which will take us to a standard normal distribution, which is totally known. Tables are available. Okay, Z. So this is, as you know, standard normal curve. Standard normal curve. Now, using the standard normal curve, we can find out any sort of probability. What is the first probability? X is greater than, first probability, this first question is this, X is greater than 75.6 something hours. So, if you see on the slide, it is converted to Z. Say X minus 100 upon 20 greater than 75.6 minus 100 upon 20. So this will be, therefore this will be equal to Z greater than something. That value has been tabulated on the slide. Okay. It is, I think, in example 3. Yes, it is some value minus. It is what? Minus 1.22. It is minus 1.22. And we can make use of table again, minus 1.22, obviously on the left side, and we want this area. We want this area. This to the right of minus 1.22, but table doesn't give you this value. Table gives you from minus infinity to minus 1.22. So what should we do? Actually, we should subtract what is the table, whatever is the table area, minus infinity to minus 1.22. That area should be traced from the table, and that should be subtracted from 1 to get the desired probability. So that probability comes out to be equal to 0.89. So there is a, in fact, if I buy a new transistor from the market, there is a 89% chance that it will last more than 75.6 hours. Last more than 75.6 hours. Okay. Now there are some other questions also of similar type. We can see on the slide. Second question is, these also have been calculated. Next slide, please. Okay, solutions are there. A new transistor will last between 90 and 110 hours. That also is there, and both are converted. Okay, now let us go to example number 4. First, please read the question. Entry to a certain university is determined by a national test. Now you see that for professional examinations like chartered accountancy, etc., you must, I think you know that there is no fixed criteria for passing standard. If they want 2% result, they can get 2%. If they want 4% result, they will publicize only 4% result. So passing standard is not fixed. Read the data. Entry to a certain university is determined by a national test. The scores on this test are normally distributed scores, means marks, they are distributed normally with a mean of 500 and standard deviation of 100. Okay. Now there is a student, Aditi, wants to be admitted to this university, and she knows that she must score better than at least 70% of the students who took the test. So she must score more than 70% of the scores, 70% of the students who have scored. Actually, X means score on this test, and it follows, we know that it follows normal distribution with these two parameters. Okay, so it is known. Centering is at V and it is fine. Sigma is 100, suppose. This is ordinary normal curve. Now, as you can see that to the left of 500, 50% of the students will be there. Remaining 50% of the students will have scored more than 500 because 500 is the mean. And of course it is median also. Therefore, if 10,000 students have given an examination, 5,000 students will have obtained less than 500 marks and remaining 5,000 students will have obtained more than 500 marks. Actually, we want to, any student or any aspirant should score more than the score which have been scored by 70% of the students. So this area is 0.5, this area is 0.2, so total area is 0.7. So this amounts to the 70% of, this represents the scores, spread of scores of the 70% of the students. Only 30% of students have scored more than this value. So this value is x0. So as I have written on the slide. Okay, next. Okay, x0 is somewhere that point. Corresponding to x0 we can find out z0 also. Now what is x0? I have written that minimum score on the national test which ensures admission to this university. This is the minimum score which an aspirant must score so that he or she can get admission to this reputed university. This is the minimum score. Now Aditi must score better than x0 to get admission. We want to find x0, which is the minimum score which will ensure the admission to this university. So this is a normal typical application because only 30% result is out. Remaining 70% are fail. Although they might have scored better than the average, still some of them will fail. Only 30% are fortunate enough to get admission to this university. So she must score more than x0. So corresponding to x0, if you go to standard normal, we will see on the slide that x0 is converted to z0. Next slide. X0 is this picture. X0. That's previous slide, please. 500 is the center. X0 is the minimum threshold limit, and x transformed to z will yield when x equal to 500, z will be equal to 0. Next slide, please. And when x equal to x0, z0 will be there. x0 minus 500 upon 100. That is z0. So corresponding to 500, we have got a corresponding curve. It is a standard normal curve. Corresponding to this point, there will be a 0. And corresponding to this point, there will be some point z0 on this standard normal curve. Standard normal curve. Corresponding to x0, we have associated value z0. Corresponding to 500, we have associated value 0. Now, from standard normal table, we can always find out what is the area. This area is known to you. You know this is 0.5, this is 0.2. So, corresponding to 0.7, using the cumulative standard normal distribution table, we can find out z0. So, that value has been determined using the table in a reverse way. Actually, we know the area, we know the probability. You locate the value of ordinate in a reverse way, and that we can see on the slide that z0 turns out to be equal to, it is equal to 0.525. Okay, 0.525. So Z0 is 0.525, and there is a relationship between Z0 and X0 minus 500 upon 100 is equal to Z0. And this turns out to be equal to 0.525, and therefore if you simplify, you will get X0 is equal to, take that on this side, and you will get, I think, 552.5. It is 552.5. It is 552.5. So this is the minimum score which an aspirant must score to get admission to this university. Now Aditi's score happens to be equal to 585, and it is very much better than 552.5, so she would be admitted to this university. 585 is very much greater than 552.5, so she is damn sure to get admission into this university. Okay, this is another application where you know that sometimes results, you know, in general examination, university examination, 40% mark pass. It is not like that. In certain examinations, certain reputed universities, they decide on the basis of the strength of the students they want to recruit, they want to admit. So only 30% of the aspirants they want to admit, and therefore in this way we can find out the threshold limit using the normal distribution. Normal distribution is applied in farms also. Normal distribution can be applied in farms also. For example, a farmer grows potatoes. Farmer grows potatoes. And suppose he fills these potatoes in different bags. The bag is designed to carry on an average 25 kilos of potatoes. But he fills the bags with potatoes without weighing. Actually, he doesn't weigh. And standard deviation is suppose 0.6 kilos. There is a variation of standard deviation is 0.6 kilos. Using this, he can determine how many bags will be underweight, what percentage of bags will be underweight, what percentage of bags will be overweight, etc. We can determine using the normal distribution. Okay. So, normal distribution, this way I have tried to explain through some examples. One example is also for practice. Example number 4. Example number 5. This also similar type of example. Aditi's example, just we saw example 4. Similar type of example is there. Okay. And next is, this is a property of standard normal or normal distribution. You can see, as I told you, mu minus 3 sigma and mu plus 3 sigma, 99.73% area is there. And several other applications we can see next time. That is during the next lecture. Other applications we can see. Why normal distribution is regarded very important? Because of its suitability in a variety of real life situations. Normal distribution is highly applicable across many areas. And the second thing is many discrete distributions, many continuous distributions, just like chi-square t, continuous distributions like chi-square t, discrete distributions like binomial Poisson, etc. They all tend to normal under certain conditions. So binomial distribution, we will see in the next lecture that binomial distribution is very difficult to use under certain conditions, and then we have to go make use of normal approximation. And how normal approximation is closer to the binomial situation, we can see during the next lectures. So all the applications, it is normal distribution is regarded as the most prominent distribution because of its applicability. Okay, and next slide please.
મિત્રો આ સેશન તમને ખૂબ જ ઉપયોગી એ સંદર્ભમાં નીવડ્યો છે, કારણ કે નોર્મલ ડિસ્ટ્રીબ્યુશનની ખૂબ જ સારી સમજ, ખૂબ જ સુંદરતાપૂર્વકની સમજ, ખૂબ જ ઉદાહરણો સાથેની સમજ કદાચ તમારા અભ્યાસ માટે ખૂબ ઉપયોગી નીવડશે એવી શુભેચ્છા. અને આવતા લેક્ચરમાં આપણે ફરીવાર અંકિતભાઈ સાથે મળશું અને એમની પાસેથી કેટલીક નોર્મલ ડિસ્ટ્રીબ્યુશન વિશેની વધારે માહિતી
college.